In this video, we're going to investigate an advanced integration technique called integration by partial fractions. And we'll do so with the following example: the integral of 10 over the quantity x squared minus 4x minus 5. Now at first glance, this might seem like a problem that we can complete by u substitution if we set u to equal that denominator x squared minus 4x minus 5. However, what we're looking for u substitution in this case would be the derivative over the function. But the derivative of that denominator is 2x minus 4. And there's no easy way to transform a 10 into a 2x minus 4. This probably isn't u substitution. So instead, what we're going to do, and the only thing we can really do with this function, is factor that denominator. In this case, it does factor into x minus 5 and x plus 1. And why these factors are going to become important? If we think about this whole fraction, and if we thought about each individual factor from the denominator, if we could get into a situation where we had just a constant value over either one of those factors, each of those being a first-degree polynomial, if we had a constant over either factor, then they could be integrated by using the natural log function. And so that's what we're going to look to do. We're going to look to take this 10 over x minus 5 times x plus 1 and break it apart into two separate fractions, kind of going from a common denominator to two different denominators. One of them being a over x minus 5 plus b over x plus 1, where a and b are both constant values. Now if we think about these two separate fractions and recombining them into one fraction with a common denominator, it would involve multiplying the first fraction top and bottom by x plus 1 and the second fraction top and bottom by x minus 5. And so when we think about recombining those fractions, that 10 from our original numerator had to have come from a times the quantity x plus 1 plus b times the quantity x minus 5. Now, in order to find the values for a and b, there's going to be two methods that I'll show you throughout this video. And the first method to solve for those constants is to use a system of equations. So we're going to go back to our original equation, and the first thing we're going to do is we're going to distribute and get that 10 equals ax plus a plus bx minus 5b. And in order to set up the system of equations to find the constants, the first equation that we'll get is that a plus b must equal 0. And that's because there is no x term in our original numerator. The ax plus bx must have canceled each other out. And our second equation will be that a minus 5b equals 10. The constants yielded the constant value of 10. And this system can be solved by elimination by subtracting the second equation from the first, which will yield that 6b must equal negative 10, and b itself equals negative 5/3. Substituting that back into either equation, I'm going to choose the simpler one that we started with. A minus 5/3 must equal 0, and so a itself must be a positive 5/3. And we can now complete what's known as a partial fraction decomposition. Our original function can now become the integral of 5/3 over x minus 5 plus negative 5/3 over x plus 1 with respect to x. And then using some properties of integrals to transform this, our first term will become 5/3 times the integral of 1 over x minus 5 dx, and our second term will become negative 5/3 times the integral of 1 over x plus 1 dx. And that is now an easy problem to integrate at the end. This will become 5/3 times natural log of the absolute value of x minus 5 minus 5/3 times the natural log of the absolute value of x plus 1 plus c, because this is still an indefinite integral. And this result, via integration by partial fractions, will represent the integral for 10 over x squared minus 4x minus 5. And the big thing to recognize is that most of this is just an algebraic process, breaking apart one fraction into multiple fractions via partial fraction decomposition. And this allows us to create an easier problem to integrate. And so we'll finish with one more example. Let's look at the integral of 5x plus 4 over the quantity 2x squared plus 3x plus 1 with respect to x. Now for a function like this, it's not a bad idea to still try u substitution, but the derivative of the denominator in this case is 4x plus 3. So this can't be u substitution because it's not a u prime over u situation. Instead, we'll try a partial fraction decomposition, which will work if I can factor the denominator. And the denominator here does factor into 2x plus 1 times x plus 1. And just a reminder about why we're doing this. We're doing this so that we can hopefully get a constant over some first degree polynomial so that we can use the natural log in integration. So we'll ignore the integral for now and just focus on the algebra we have to do to complete this problem. Taking this more complicated fraction and trying to break it into two fractions, one with a constant a over 2x plus 1 plus a constant b over x plus 1. Thinking of what would happen if we recombine these fractions, that 5x plus 4 in the numerator must have come from the constant a times x plus 1 plus the constant b times 2x plus 1. Now I did mention earlier that I was going to show two methods for solving for these constants. The first one was solving by a system of equations, so if you're comfortable with that, you can just keep using that method. But method 2 for finding the constants, that will involve using the roots for each of those factors from the original denominator. And we do that in order to eliminate one constant at a time to solve for the other. So we'll start by focusing on the factor x plus 1 and use its root. We're going to substitute in an x value of negative 1. And this will yield 5 times negative 1 plus 4 equals a times 0, because we plugged in the root to that factor, plus b times the quantity 2 times negative 1 plus 1. And simplifying this equation down, we will get that negative 1 must equal negative 1 times b. Plugging in negative 1 eliminated a from the equation, and we end up with our constant b equals positive 1. And we'll do the same thing with the other root. 2x plus 1 has a root when x equals negative 1/2. So we'll sub a negative 1/2 into the equation, get 5 times negative 1/2 plus 4 equals a times negative 1/2 plus 1 plus b times 0, because we plugged the root into that other factor. And this will simplify to 3/2 equals 1/2 times a, and a will equal positive 3. We now have our constants, so we can complete our partial fraction decomposition. The integral of 5x plus 4 over 2x plus 1 times x plus 1 with respect to x can be broken into the integral of 3 over 2x plus 1 plus 1 over x plus 1. Now we do want to be careful here, realizing we are going to get natural log functions out of this, but we should still be thinking through u substitution. On the first fraction, u equals our denominator 2x plus 1, and its derivative would be 2 dx. Well, that must mean on the antiderivative from chain rule that we had a times 2, which means going in reverse, we're going to need a 1/2 out in front of this integral. And with that taken care of, the integral for our first fraction becomes 1/2 times that 3 from the numerator times the natural log of absolute value of 2x plus 1. We don't have to concern ourselves with u substitution on the second fraction, because the derivative of x plus 1 is just 1. That integral becomes the natural log of absolute value of x plus 1. And just make sure to remember the plus c for the indefinite integral. So just simplifying this a little bit more, we will get a final result of 3/2 natural log of 2x plus 1 plus natural log of x plus 1 plus c. Now on the surface, this integration technique might just look like a lot of algebra, and it might be tough to see the application attached to it, but the biggest application is being able to work with any differential equation where the derivative is set up as a fraction. It allows us to expand on what we've seen from u substitution and add in one more technique. And the biggest application for this particular technique is in development of the logistic growth model, which will be a separate video from this one. Your goal should be to make sure that you are comfortable with integration by partial fractions before moving on to applications like that one. Thank you for watching.